Assalamualaikum warahmatullahi wabarakatuh, and hi again. In this video, I'm going to share with you a number of examples on how to perform statistical tests of hypothesis on the difference between two population means mu1 minus mu2. Hopefully at the end of this video, you will get a clearer picture on this topic and be able to achieve all these topics' learning objectives. Let's proceed to the first example in the next slide. Please refer to test 4.9 in page 99 from Statistics for Engineers textbook. Having a question like this, again, we need to recognize the information given in the question and write this information using correct notations. What do we have? From the sample data of two groups of engineers, we have information from group 1, such as the sample size 35, the mean score 82, and the standard deviation 5. So we can write down this information like this. N1 is 35, X bar 1 is 82, and S1 is 5. Similarly, we have the sample information from the second group, such as the sample size 40, the mean score 77, and a standard deviation of 10. This information can also be listed like this. N2 is 40, X bar 2 is 77, and S2 is 10. What else do we have? Look at the question again. Is there any difference between the performances of the two groups? How do we usually measure performance? Of course, through the mean scores, right? So the question implies, is mu1 different from mu2? That is mu1 minus mu2 different from 0? Therefore, the parameter of interest we want to test here is mu1 minus mu2. So what do we have to figure out further? Surely, which of the 5 cases should we use, right? First, look at the population variances, sigma 1 squared and sigma 2 squared. Do we know the values of these population variances? If you browse through or look through the question again, these values are not stated anywhere in the question. Do you agree? So, sigma 1 squared and sigma 2 squared, or sigma 1 and sigma 2 are both unknown. Next, look at the sample sizes. We have noted earlier that N1 and N2 are both large. Furthermore, from the question again, the population variances are assumed to be equal. Therefore, we will use the pool variance as p squared to estimate these two unknown and equal population variances. Having all these 3 conditions listed, that is, the unknown population variances, the large sample sizes, and the assumption on equality of population variances, we can now identify the suitable case to solve the problem. That is, to use case 2a, which involves a z-test statistic. Since we want to test if mu1 is different from mu2, or mu1 minus mu2 is different from 0, then we have a two-sided test which should be performed at the level of significance alpha equal to 0.05, which is illustrated further in the next slide. We continue resolving the question from task 4.9. As mentioned earlier, the question asks if there is any difference between the performances of the two groups of engineers, that is, if group 1 overall or population mean score mu1 is different from mu2, which is the group 2 population mean score. The keyword difference should be under H1, but please remember, when writing the statements, it must be the null hypothesis H0 first, followed by the alternative hypothesis H1. Therefore, we can write the hypothesis statements as follows. H0, mu1 is equal to mu2, or mu1 minus mu2 is equal to 0, whereas under H1, mu1 is different from mu2, or mu1 minus mu2 is different from 0. Since we have a two-sided alternative hypothesis test, then we can write the rejection rule as follows. Reject H0 if the modulus of Z test is greater than Z alpha over 2, which is Z 0.025, that is 1.96. Remember, in case 2a, we use the pool standard deviation in the Z test formula. Therefore, we need to calculate the pool standard deviation first, which is the square root of the pool variance given as follows. Substituting all required values, you will get the pool standard deviation to be 8.0665. Once we get the pool standard deviation value, we can substitute this value into the Z-test formula written like this. Please notice that the value of mu1 minus mu2 under H0 is 0. Again, by substituting all required values in the Z-test formula, you can check that the Z-test value is 2.6780. Now we can compare the modulus of Z-test with the critical value 1.96. Obviously, the modulus of Z-test, which is 2.6780, is much greater than 1.96. Hence, we can decide to reject H0 and conclude that the sample data provide a strong evidence at 5% level of significance, or alpha equal to 0.05, that mu1 is significantly different from mu2, which implies that the performances of the two groups of engineers are evidently or significantly different. Now look at exercise 4, question 13 on page 108 of Statistics for Engineers textbook, where the question is modified slightly in this video. The modified question is, determine whether soil of type S1 has a higher gamma radiation dose compared to that of type S2. As usual, we need to recognize the information given in the question and write this information using correct notation. Based on the sample data from the two types of soils, we have information from type 1, such as the sample size, the sample mean, and the sample standard deviation. So we can write down the information like this. N1 is 6. X bar 1 is 7.52 and S1 is 0.024. Similarly, we have the sample information from the second type, such as the sample size, the sample mean, and the sample standard deviation from the second sample. So again, we can write this information as follows. N2 is 5, X bar 2 is 7.49, and S2 is 0.032. Next, look again at the question. Determine whether soil of type S1 has a higher gamma radiation dose compared to that of type S2. So the question implies, is mu1 greater than mu2? That is mu1 minus mu2 greater than 0? Therefore, the parameter of interest we want to test here is mu1 minus mu2. What else do we need to know? Of course, we need to identify which of the 5 cases we should use to solve this question. As before, first look at the population variances, sigma 1 squared and sigma 2 squared. Do we know the values of these population variances? These values are not explicitly stated anywhere in the question, right? So, the population variances sigma 1 squared and sigma 2 squared are unknown. Next, look at the sample sizes. We have noted earlier that N1 and N2 are both small. Furthermore, from the question again, the population variances are assumed to be equal. Therefore, we will use the pool variance as p squared to estimate these two unknown and equal population variances. Now we can identify the suitable case to solve the problem, that is, to use case 3a, which involves a t-test statistic. Since we want to test if mu1 is greater than mu2 or mu1 minus mu2 is greater than 0, then we have a right-sided alternative hypothesis test which will be performed at the level of significance alpha equal to 0.01. The complete solution is discussed in the following slide. Let's look at the complete solution for exercise 4, question 13, which has been a little bit modified. Recall the modified question is to determine whether soil of type S1 has a higher gamma radiation dose compared to that of type S2. The keyword higher refers to greater than and should be under H1. Therefore, we can write the hypothesis statements as follows. H0, mu1 is at most or simply equal to mu2, or mu1 minus mu2 is equal to 0, whereas under H1, mu1 is higher or greater than mu2, or mu1 minus mu2 is greater than 0. Since we have a right-sided alternative test of hypothesis, then we can write the rejection rule as follows. Reject H0 if t-test is greater than t alpha nu, which is t 0.019, given by 2.821 from table 5 in statistical table booklet page 35. How do we know that the degrees of freedom nu associated with the critical value is 9? The answer is simply because we have case 3a where nu is defined as n1 plus n2 minus 2, that is 6 plus 5 minus 2, so we have nu equal to 9. Using case 3a also, we need to use the pool standard deviation in the t-test formula. Therefore, we need to calculate the pool standard deviation first, which is the square root of the pool variance given by 0.02784. After getting the pool standard deviation value, we can then substitute this value into the t-test formula given by this expression. Again, please notice that the value of mu1 minus mu2 under H0 is 0. By substituting all required values in the t-test formula, you may want to check if the t-test value is 1.7795. Now, we can compare the t-test value with the critical value 2.821. We can clearly see that the t-test value is 1.7795, which is much smaller than 2.821. Hence, we can decide not to reject H0 and conclude that there is no strong evidence at 1% level of significance or alpha equal to 0.01 that mu1 is significantly greater or higher than mu2, which implies that the soil of type S1 does not have a significantly higher gamma radiation dose as compared to that of type S2 at 0.01 level of significance. Now, suppose question 13 from exercise 4 is further modified, where other things remain unchanged. We assume that the population variances are equal to 9 times 10 to the power of negative 4, or simply 0.0009. How do you tackle this question? Is it still case 3a? Of course not, because we know the values of population variances, which are 0.0009, right? Without worrying whether the sample sizes are small or large, and we do not even have to use the pool variance, This is obviously case 1, which makes use of the primary z-test statistic and will be compared with a right-sided z-critical value at alpha equal to 0.01. Continue with the solution for question 13 from exercise 4 that we have further modified. We will use exactly the same H0 and H1, but since this is case 1, then the rejection rule is reject H0 if z-test is greater than z0.01, which is 2.3263. Here, z-test is defined as the difference between the sample means minus 0, which is the value of the difference between the population means under H0, divided by the square root of the sum of the known variances over their corresponding sample sizes. You can check the value of z-test is 1.6514. The decision and conclusion are the same as before, although we use z-test this time. One important lesson that we learned here is to identify a correct case and use a suitable test statistic when solving a problem on testing the difference between the population means mu1 minus mu2. Let's look at another example. A frontline production supervisor in a particular industry claims that morning shift employees are more efficient, that is, work faster than the evening shift employees. To investigate the supervisor's claim, a quality control engineer observed assembly times in minutes spent by 12 randomly selected morning shift employees and 17 randomly selected evening shift employees, and summarized his observation as follows. Assume that the assembly times are normally distributed. Test at 5% level of significance whether the data observed by quality control engineer provide any evidence to support the supervisor's claim. Suppose sample 1 refers to data from morning shift and sample 2 from evening shift. We can list down N1 equal to 12, X bar 1 equal to 20, and S1 equal to 2.7. Likewise, we can also list down N2 equal to 17, X bar 2 equal to 23, and S2 equal to 4.3. Next, what is the problem we want to solve here? Yes, we are to perform a hypothesis test, but what parameter do we want to test? Here we want to investigate if the data observed by the QC engineer provide any evidence to support the supervisor's claim that morning shift employees are more efficient, that is, work faster than the evening shift employees. What does it mean? Work more efficient or faster in terms of assembly time? Does it not imply that the average assembly time taken by morning shift employees is shorter or less than the assembly time taken by the evening shift employees? That is, we want to test if mu1 is less than mu2 or mu1 minus mu2 is less than 0, right? Therefore, we need to identify which case we should use here. I always begin with the population variances. Do we know the values of these population variances, sigma 1 squared and sigma 2 squared, or population standard deviation, sigma 1 and sigma 2? Not mentioned anywhere in the question, right? So, the population variances are unknown. Next, look at the sample sizes. Yes, both sample sizes are small. So, we have to use case 3, which involve a t-test statistic. But which one? Is it case 3A or 3B? Look again at the question. Is there any assumption on population variances mentioned anywhere in the question? What we only know is that the assembly times are assumed to be normally distributed, and that's it. Since the assumption on equality of population variances is not stated explicitly in the question, we can assume that sigma 1 squared and sigma 2 squared are unequal. Therefore, we should use case 3b to solve this question. Proceed with solving the extra example where we want to investigate whether the data observed by the QC engineer provides any evidence to support the supervisor's claim that the morning shift employees are more efficient, that is, work faster than the evening shift employees at 5% level of significance. In terms of the assembly time, the statements of hypothesis can be written as follows. H0 mu1 is at least or simply equal to mu2, that is, mu1 minus mu2 is at least or simply equal to 0, which implies the morning shift employees are just like evening shift employees or work less efficient, that is, on average, the morning shift assembly time is just the same or longer than the evening shift assembly time. On the other hand, the alternative hypothesis H1 can be written as mu1 is less than mu2, that is, mu1 minus mu2 is less than 0, which is exactly the supervisor's claim that the morning shift employees work more efficient than the evening shift employees, implying that the morning shift assembly time is on average less than the evening shift assembly time. So we have a left-sided alternative hypothesis test. Since we knew in the previous slide that we have case 3b for solving this question, therefore the rejection or decision rule is reject H0 if t-test statistic is less than the left-sided critical value, which is negative t0.0527 given by negative 1.703. How do we get the degrees of freedom nu equal to 27? Remember, in case 3b, where the population variances are unknown, the sample sizes are small, and more importantly, the population variances are assumed unequal. The definition of degrees of freedom is not straightforward, as given by this expression, where you can refer to the statistical table booklet to obtain this formula. Substituting all required values in the formula will give you nu around 26.7. By rounding off this value to the nearest integer, then we have the degrees of freedom nu equal to 27. Having identified the critical value, now we can calculate the t-test value using this formula. Please check that the t-test value is equal to negative 2.3042. What can we decide? We can see that the t-test value is obviously smaller than the critical value, which suggests that we can reject H0 and make a conclusion that the data observed by QC engineer provide a sufficient evidence at the level of significance alpha equal to 0.05 that mu1 is evidently less than mu2. In other words, the sample data provide or support the supervisor's claim that the morning shift employees are more efficient, that is, spend less time on assembly than the evening shift employees. Please note that the value of mu1 minus mu2 is not necessarily 0 under H0 as given in all examples that we have done in the previous slides. At times, you can also have a scenario where the difference in the population means is not 0 under H0. For example, you might want to test if the difference between the population means is at most 3. How do we write down the null and alternative hypothesis? And how do you define your test statistic? To answer the first question, H0 can be written as mu1 minus mu2 is at most 3, and H1, mu1 minus mu2 is greater than 3. Hope by now you already get the idea why we use less than or equal to under H0 and greater than sign under H1. But what I want to highlight here is the value of the difference between mu1 and mu2. You can see here that the value is not 0 anymore but 3. The second question, what is the test statistic? For any of the 5 cases in this topic, the test statistic should be defined as the difference between the sample means x bar 1 minus x bar 2 minus 3, which is the value of the difference between mu1 and mu2 under H0, divided by the denominator, which depends on the selected case. Again, what I want to highlight here is this value 3. It is not simply 0 as in the previous examples, but 3. Therefore, please be careful when you want to write down the hypothesis statements and calculate the test statistic, because in this simple example, many students have made such trivial careless mistake in the past. Having explored on a number of examples on testing the difference between the two population means, we are now at the end of this topic session. Before I end this video, as usual, let us do a checklist on the attainment of this topic's learning objectives. At the end of watching and listening to this video, that is, at the end of learning this topic, are you now able to perform a statistical hypothesis test on the difference between the population means mu1 minus mu2? The testing procedure is exactly the same as the procedure for testing single parameters. The difference is only on the parameter that you want to test, which will influence the choice of test statistics and critical values. Next, are you now able to classify the 5 cases on testing mu1 minus mu2? Remember, when you want to choose a suitable case, always look at the population variances first, not the sample sizes, whether these population variances are known or not, before identifying which case is suitable to solve a particular problem. If the population variances are both known, immediately this is case 1, which involve the use of exact test statistic. If not, then only you can look at the sample sizes for the other 4 cases. Next, are you now able to identify a suitable test statistic and calculate its value correctly? If you can achieve the second objective, I believe you will certainly be able to achieve the third objective. What about the fourth and the last objective? If you are able to make a statistical decision correctly and write a practical conclusion, I am sure and very certain that you should be able to describe a meaningful comparison between the two population means. I think that's it for now, guys. I'll see you again in the next video on other topics. Until then, Assalamualaikum warahmatullahi wabarakatuh, and thank you for watching.